Our next speaker is Guy Gilboa from the Technion, and this is a joint work with his student Jonathan Brokman, Eyal Gofer, and Elnatan Kadar.
Elnatan, yeah. Hi, so I'm Guy Gilboa from the Technion, ECE, and the Jonathan could not come today, so I'll present it. It's with Jonathan Brokman, Eyal Gofer, and Elnatan Kadar. Jonathan is a PhD student, Eyal research fellow, and Elnatan is a MSc student. So it's a little more conceptual talk. I try to, okay, something that we have mostly, probably every one of you who ran neural networks is this branching effect or branch specialization. We try to tackle it and see what we can say about it. So these all, we have things, okay, that run in parallel, get the same input, and produce something else. And we have, so they look very similar in the architecture, but produce different things. So this is a very known phenomena in neural nets that, okay, you put similar architectures in parallel, and every one of them will produce different, this is like the beginning of a network, so the things that were noticed in ImageNet very early on, so you have different filters, etc. And the question is, why, and does it happen every time? Are there some conditions? So we can answer a little of it today, and can we apply it to something? So let's start with that specialization is basically good, okay? And we get it somehow here for free without doing anything. So how can it happen? So like doctors, okay, so we are specialized in cars. Everywhere around us we have special people, special companies, etc. So it's something very useful, of course. Okay, so we just narrowed it down to a very, very simple architecture. Okay, we have, so this is the architecture. We have the same input. We have many nets, so we are analyzing it in a macro fashion. So we have a neural net. It's not like a perceptron or anything. You have these outputs. They are just summed and produce an output. So it's same input, same architecture, simple summation to obtain the final output, and the only difference between those networks is just the random parameter initialization. So how come they give different results? Okay, it's somewhat surprising. So let's see. So if you can like try this at home, not dangerous. Okay, so we just took ResNet 18, scaled it down 100 times less, so just 80K parameters. We'll see later where just the small networks give you very good this specialization. We had 16 branches, and let's see what we get. So we had like very interesting phenomena in branch specifically 10 and 14. So we just took the first 1% of the most confident responses for a horse that branch 10 did. Then we said, okay, what branch 14 did? Okay, so his horse is this one. This is CFR10, by the way. So it's very small images, but I think you can see that there is a very, very significant difference. So you see specialization, right? Branch 10 specializes in the head of the horse, and 14 in the full horse. And if we go to the deer, the same branches. This is the close-up, and this is sort of the long shot. Okay, so we actually didn't do anything. It's the same networks, exactly same architecture, same input, etc. So let's first define specialization. What we mean by this. And we define it mathematically. I'll just show an example. So we have like 3 examples here, 3 inputs. It's a horse from close range. So branch, let's say we have just 3 branches and 2 classes for simplicity. We just want to distinguish between a horse and a bird, and this branch says, okay, I'm quite confident it's a horse. And the second one says, I don't know, and this third one also. And the faraway horse, okay, he is really identifying this horse, the other not. And the last branch, okay, distinguishes very well between a bird but doesn't know too much on horses. Okay, so this thing we call specialization. It's not class, it's instance type. So for specific images, they can tell, they know more. Let's give an example of bad specialization. So this is highly specialized network. And this, okay, so it doesn't matter the accuracy here, it's just if they agree together or not. So here, all of them say horse. Here, all of them don't really know. Here, all of them say bird. So basically, it's low specialization. And then we just formulated here. It's, I don't go into the specific definitions, okay? So how do we analyze the underlying mechanism? So we are using similar techniques that were mentioned earlier of wide neural networks, a linearized model, and we can analyze something. So it's basically a first-order Taylor approximation of the network, and with a linearized network. So basically, it's still general enough because it's any network can have a linearization. So it doesn't take care only on specific architectures. And then you can analyze just by linear algebra, so you have all the tools you want. Okay, so I'm just going to show you a little, okay, I won't go into the mathematical things we did, but just a little intuition of what's happening. So if you have a small network, basically, we are in this, some sort of feature space. So basically every branch, so let's take the first branch, is spanning a small subspace of the entire embedding space, basically. Okay, so let's say branch 0 is spanning such space that this instance of a horse appears there, and the second branch takes part of this one, the third one, the bird appears in it, and as you see, they don't have many parallel areas, regions between them. Okay, so this is basically our intuition of what's happening underneath the network. So this surprising effect of random initialization, every branch has sort of conquered a little space in the embedding space and is very good there, doesn't know much on the other ways, and is more or less staying there. So the initialization is very, very important. And they most probably do not overlap. So I'll take you a little more to beyond the analysis to what can be done and some new ways to look at things. So we took it from classifications now to GANs, or in general generative models. I'm not using diffusion, but old-fashioned GANs by today's standards. So let's see, we have like F, some image, some signal. So we can decompose it like in a traditional way where we did in undergraduate courses to Fourier, so fire some elements, atoms, frame, wavelets, etc., dictionary learning. And we can see the resemblance that these branch neural networks basically also give us a sum. So if we do it in a sort of an encoder-decoder fashion, so we give it F and tell it approximate F by these networks that do a generative model, and then the sum of them will produce F again. So it's a little more complicated than that, but this is basically what's underneath this example. So let's go to the linear. Okay, this is classical, no neural net, so it's just Fourier. You have like low pass, band pass, and high pass. So the sum of them produces the B above. And this is like earlier studies I did before with nonlinear decompositions. Sharper based on total variation, the sum produces the input image precisely. Now we go to style GANs and see how we can do it again with branch specialization. Okay, I have 3 minutes or something. Let's hope. Okay, so let's take branch style GAN. So I hope all of you know. So it takes this input, bottom is output. Okay, so this is real, this is generated. So it's based on star GAN basically, but it's a branch thing. And here is how we can produce from this GAN sort of a phase transform, you can say. So it's the images that you see, the three faces there, are decomposed here into 9 channels. We can say it's like the basic elements of faces of this specific training set, etc. It's celeb A, HD, doesn't matter. But okay, so you see that it's decomposing. So this is a specialization. So each GAN is specialized in different features. You see texture, you see lighting, you see the mouse, etc. So what can we do with it, for instance? So we can use this sort of transform or decomposition and do some unsupervised segmentation, because the decomposition makes it so simple now, so the mouse can be even segmented by classical methods, because it's very, very simple. This is like a cat of an eye problem, so it's like a sort of self-supervised way to do segmentation. Where can we use it more? So we call it form classification to detection, and this is the concept. This is a toy example. In class 1, we have blue, white rectangles. In the second class, we don't have, but we don't have pairs. And we have some generative models. We want to detect those things. We have generative models that work like this. Here is it, like a guided branching system. So for the first class with the rectangles, it produces from both the 3 channels and the right class from the 2 channels. And then the upper channel actually is the thing that we want to look for. It's these white rectangles. So we call it a class differentiator. So what can we do? This is a grant we recently got from the Ministry of Science to detect fractures in a sort of self-supervised way. So form classification, which the doctors, it's easy to classify, but very hard or harder, much more time to give specific pixel detection or segmentation. And here the generative models were able to fill up the fractures, and then we can do some heat maps, and in the red is the ground truth, and this is what we found. So we automatically can pinpoint the places of the fractures. Almost finishing. So the last slide is, this is just a toy of, okay, so what is the class differentiator between men and women, for instance? Okay, so you can do a lot of toys with it. So this is like 2 women, and the class, the channel that differentiates them from men is this. Okay, so for instance, see, so eyelashes, etc., are very important. Mouth, of course. Okay, the earring, etc. And what is not important is the color of the skin or the lighting. Men and women have similar things. Okay, the background is not important, etc. And this is for men. And similar thing, okay, mustache, beard, mustache, etc. And eyebrows, very chin, so on. So I'll wrap it here. Thank you.